Let's take a short digression and discuss why we're building a model. In fact, this is a very important question because the answer to this will determine how we validate our models. We have discussed various models that we built and the ways we can quantify the errors in terms of the loss function for each model. We have also encountered various ways to calculate the loss function of each model. We have seen that the choice of the loss of the risk function is dependent on how we formulate the problem. In fact, we are free to choose our loss or risk function, and a judicious choice of a loss or risk function can result in a well-performing model. Now, this choice is very dependent on the problem formulation. The problem formulation itself is in turn dependent on this question of the purpose of the model itself. In natural sciences, we often build very well-behaved, sometimes linear and first order in time, models with simplifying assumptions of the parameters. In this case, a good fit to the model parameters, often they are point values, is desired, and we find the best fit of the parameters to the data. This is often referred to in fields like economics and many branches of engineering as the model identification problem. In statistical learning, we accomplish more than just identification. We choose systems that are quite complex and often models with many non-linearly correlated variables to describe them. In this case, we want to recognize the patterns in the data, to not only solve the identification problem, but also to accurately predict such patterns for all possible future data where the patterns are similar but not necessarily the same. Validating a statistical or machine learning model thus not only requires us to validate the model on the data we have, but also to hedge the model's prediction abilities with probabilistic bounds.